fake compact Hermitian symmetric spaces.
Yes, I'm really glad to be speaking on this topic because it actually, my work on this began while I was here last time, 7 years ago, and a large part of it was done here, and I thank Tasso for organizing this talk. So let me begin by defining what fake projective plane is and what its natural generalization should be. So a fake projective plane is an algebraic surface which is both smooth and projective, and it's defined over C, and it's Betti numbers. So if you like, HIX R is isomorphic to HI P to C with coefficients in R, which means that the Betti numbers are 1, 0, 1, 0, 1. So the question was whether they are such surfaces, and X of course should not be isomorphic to P2. And in theory of algebraic surfaces, the classification program and so on in terms of topological invariants would like for such surfaces not to exist, for example, but they exist. And the first example was produced by Mumford in 1978 using p-adic uniformization. So he used p-adic uniformization to construct such a surface over algebraic closure of Q2 bar. You take the d-adic field, algebraic closure of that, and over Q2 bar, he constructed such a surface, and then by embedding it in C, you get a complex surface with the desired properties. And what he used was inside PGL3 Q2, you have a discrete subgroup gamma which acts transitively, in fact simply transitively, on the vertices of the building. Okay, so he made use of this. He knew existence of such a thing using some unitary group defined in terms of q square root minus 7, and he used that to.
Was that constructed by Tits? Who was it?
I do not know. Maybe he found this, but later Cartwright, Steger, Japa, and one more person. So they actually determined that there are not many such subgroups inside PGL3Q, PGL3QP. So the method of Mumford actually does not go far enough to construct all such examples. In fact, the only other such group arose from a unitary group constructed out of q square root minus 15. So to construct a unitary group, you need a base field, so which in our case here is q, and a quadratic extension, and you use the Galois-morphism to write a Hermitian form. So you have this a pair which gives rise to a unitary group, and then you can get a vertex transitive action. So this action was produced by Cartwright, Steger, and Japa, and one more person. I forget the name. So in any case, this example was then used along with what Mumford had done by Ishida and Kato to construct two more examples. Okay, and then the method stopped. So we had 3 examples, and that's it. But we also knew from rigidity theorem. So I will actually, let me not hurry up. So first of all, by the work of Yau on Calabi conjecture, so we know for such surfaces that C1 square equals 3C2, and so they are they are uniformized by a complex 2 ball. So the universal cover of such a surface has to be complex 2 ball. So let us write down B2C to our surface X, and the automorphism group of the complex 2 ball, as we know, is PU21. So this is the automorphism group. And so you will get a discrete subgroup gamma of PU21, torsion free, such that quotient of B2C by gamma will be X. So X is then B2C modulo gamma. So it's uniformized by a complex 2 ball, which is a Hermitian symmetric space arising from this real semisimple group PU21 of adjoint type. Okay, now it turns out that not only gamma is a discrete co-compact subgroup of PU21 as it should be, because this is a compact surface. So gamma is discrete, torsion free, and co-compact, but it's actually arithmetic. So gamma, which is the fundamental group of our surface X, is arithmetic in PU21. So this was proven by my collaborator. My work today is with Sai-Kee Yeung. And so this was proved independently, arithmeticity was proved independently by Sai-Kee Yeung and Bruno Klingler. Okay, so I got interested in this problem precisely because we knew from these. Pardon me? Yeah, so you see, this is a rank 1 situation where Margulis arithmeticity theorem may fail, and in fact we know that it does fail for the groups SON1 and PU21 and PU31. But the failure is because non-Archimedean superrigidity fails. Using the fact that the Picard group is computable, H1 is 0, and so on, one could prove for fundamental group of these surfaces that superrigidity in the non-Archimedean setup. That's based on Gromov-Sen. Gromov-Sen, the joint paper where they study. Yeah. So
you said Ser.
No, not Sen. Sen. The one at Ricksen.
Yeah, so this condition on the topology.
That's right.
Allows you to push through the Collet generalization.
That's right. So superrigidity in the non-Archimedean setup. You see, local rigidity. So it means that gamma can be embedded over a number field. But then you want to prove that the denominators are bounded. So, okay. So now you see the problem is following. Can we find arithmetic gamma inside PU21, which when you take quotient of B2C will give you fake projective planes. So one property of fake projective plane, of course I have enumerated the cohomology, but one property is, for example, that the chi, the Euler-Poincare of such a thing is same as that of P2, and therefore it's 3. So the question is, are there arithmetic subgroups in PU21 which have Euler-Poincare 3, which are torsion free and co-compact, and can you enumerate them all? So I have given a formula for volume of arithmetic quotients for any general semi-simple group. In fact, even S arithmetic group, and you allow function field also if you like. Then you have formula, exact formula for volume of the quotient of symmetric space or semi-simple group. It's the same thing. And this formula then with Gauss-Bonnet gives you a way to compute Euler-Poincare. So in principle, Euler-Poincare is given by a computable formula. And this formula involves many things, as we will see. So zeta functions, discriminant, class number, and so on and so forth. So you will have to then make estimates so that you are able to list the possibilities for the number fields involved, the groups involved, and so on, and finally arithmetic groups involved. And this could be done with a certain amount of work. But before I begin that work, let me first generalize this problem and show you that this becomes part of a more general question which may be of interest. So you see, I'm dealing with a semi-simple Lie group, namely PU21. It's symmetric space, which is Hermitian. And I'm looking at arithmetic subgroups, which give me some nice objects. And the nice object is that the cohomology of this object X is same as that of P2. But what is P2? See, P2 is a compact dual. So P2C is compact dual of B2C. So we are looking at Hermitian symmetric space and its compact dual. And I want quotient of this Hermitian symmetric space to have same real cohomology as the compact dual. See, one knows that for any symmetric space X, oh, I'm sorry. So now I will have to use, maybe abuse notations. Maybe I will use a script letter. So suppose I have some symmetric space X, and suppose I have a discrete co-compact subgroup in the identity component of.
Gamma go to the right. Put it on the left.
Oh, okay. So I can put it on the right, on the left. Okay. So suppose you have a discrete co-compact subgroup in the isometry group of X, identity component. Then one knows that the cohomology of gamma, or if you like homology, embeds, it contains the cohomology of the compact dual. And the compact dual is usually denoted by X sub U. You see, the point is that the cohomology of gamma, think in terms of de Rhams theorem, so it's given by gamma invariant exterior forms on X, and then you get a complex, and then you take cohomology of that. On the other hand, you can take all exterior forms which are not only invariant under gamma, but under the whole group of isometry. And that it was known to Cartan already, Elie Cartan, that consists of harmonic forms. And therefore, by Hodge theory, that then embeds the cohomology of the G invariant forms, therefore embeds in this cohomology. And that cohomology of G invariant form, the complex of G invariant form is precisely by K plus P decomposition, it's the cohomology of the compact dual. But you see, for those of you who do not know what compact dual is, think of hyperbolic space, n-dimensional hyperbolic space. Its compact dual is the sphere. So if you use K plus P decomposition for the Lie algebra, then if you replace K plus P by K plus square root minus 1P, you get a Lie algebra with compact Lie group, and the K part still is there. So this group, which came from G, gives me a GU with the same K. So you have GU mod K. So this is my X, and this is my XU. So we are looking for the following situation. You have a symmetric space, and you are looking for gamma, arithmetically defined, because that's the only thing which we can handle. And then co-compact, discrete, torsion-free, and I want the cohomology of this gamma to be as small as possible, because this cohomology always sits inside here, and I want the cohomology to be absolutely the smallest one, and which means that it should be equal. So if our X was Hermitian, then I will call this situation a fake Hermitian, a fake compact Hermitian thing. So it's cohomologically compact dual, but really not. Okay, so the question is, can we list all irreducible arithmetic, fake, compact, locally symmetric space. And for number theoretic regions, I will just concentrate on the ones which are Shimura varieties, so the ones which carry Hermitian structure. So I will just add the word Hermitian, but the problem can be tackled also in some other situations, as I will remark later. Okay, so this is the situation, and the answer is yes, and the only ones. So you see, the Hermitian symmetric spaces arise from the groups of type AN. So these are unitary. So if you like, PU M comma n plus 1 minus 1, and then BN, CN, DN, and also two exceptional ones, E6 and E7. So from Cartnage classification of Hermitian symmetric spaces, we have a complete list of which semi-simple group give you Hermitian symmetric spaces, and these semi-simple groups are all listed here.
Is it known that gamma should be arithmetic?
Yes, if the rank is greater than 1, then it's arithmetic. If rank is 1, then by definition, so I am listing only arithmetic ones. But it's not known. It's not known in higher dimension, except in dimension 2 if arithmeticity holds. I mean, there are some claims, but those have not been completely verified. Yeah, Sai-Kee Yeung has claimed that in dimension 4 he can see arithmeticity, but I don't think that it's been PU4. The topological assumption will be that the cohomology, same cohomology. Yeah. But the proof has not been completely written. Okay, so you have a whole wide variety of semi-simple groups giving rise to Hermitian symmetric spaces, and each one of them, as you know, contain countably many density commensurability classes. So you will have to deal with all of them and see which one can give you arithmetic groups with the desired property, and the answer surprisingly turns out to be rather so theorem only n with n less than or equal to 4 can give, let me not write everything, so arithmetic, fake, compact, Hermitian, etc. Locally symmetric spaces.
Can I ask a question?
Yeah.
The general picture here. So suppose instead of asking for fake projective plane, I fix the topology. I fix a Betti number.
Yeah. Oh, any Betti number you want?
Yeah, maybe instead of making 1, 1, 1, 0, 1, 0,
Yes.
1,
Yes.
I allow 2 in the middle.
Yes.
Is there any finitely many?
Yes, because as soon as the Euler Poincare is bounded,
So what you really prove is if the Euler Poincare is bounded, then only finitely many.
that's been already proven in my work with Borel long time ago.
Coming from volume.
Yeah, coming from volume. As long as Euler Poincare is non-vanishing. You see, if rank of K is not rank of
So
G.
then you could ask the question of classifying for anything, not just projective plane.
That's true, but the question will be whether geometrically it's interesting. And moreover, the cohomology is minimum in this case. So from the theory of automorphic forms and so on, you see, so which means that only certain automorphic forms exist and others don't.
I agree, but I'm just...
Sure. So in principle,
Generalize your problem.
sure. In fact, there will be one algebraic surface which was supposed not to exist, and it does exist after our work. So yeah, so this is something maybe of interest. Okay, so now, and in fact, so A2 gives us the fake projective planes and an interesting and another surface X with Euler Poincare 3, but which is not first Betti number is 2. So, and in fact, such a surface was not supposed to exist. In fact, there was a feeling, you see a surfaces of general type, the smallest Euler-Poincare array is 3. And it was thought that P2 and fake projective planes are the only algebraic surfaces which should have that property. But it turns out, because of our work, and then computations done by Cartwright in the Steger or big computers, that there is a surface which comes from the pair. In fact, these are ball quotients, so there is a unitary group involved, and the unitary group which is involved here, let me write down, I think the pair is, q square root 3 and q square root 3, q zeta 12. So you take this 12th root of unity, that will be our quadratic extension of q square root 3, and this gives you a unitary group defined in terms of a Hermitian form, and which gives you the surface. But it's intricate. I will explain to you why it's difficult to construct. Okay, so now, and so A2 gives you fake projective planes. We know the situation with A3 little bit. We have not analyzed this completely, and we don't think that we will go further in this. So for A3, so which means that you have a semi-simple group which is product of groups of type A3. So it could be SU31 and SU22, PU, let's say. So I am looking at only the adjoint type, because isometric group is of adjoint type. So you have a mixture of these groups, so product of such groups, and they give you symmetric spaces of type A3. And now the arithmetic group will arise from some structure over a number field, and this number field I will call K, which is the base field, and it will be given by a quadratic extension because you have a unitary group involved, and K will be totally real and L will be totally complex. So, the reason for that is that this group and its compact dual, they all require, over reals, are given by the pair R and C. So PU31 over reals is given by the pair R with C, the usual involution of C over R. And the compact dual group of this is PU4. So that also requires R and C. So the field K and L, this is a number field and this is a quadratic extension, and this number field will be totally real, and L has to be totally complex because of that reason. And in that list of Bn, Cn, Dn, this is not often the case. For Dn, it could be sometimes totally real field and a quadratic extension which is also totally real, and sometimes it could be totally complex. So depending on the parity of n. But in any case, here in case of A2, A3, A4, and so on, it's always a totally real field and a totally complex extension. Okay, so now the fields involved for A3, which so the degree of K over Q is less than or equal to 2. So we have, after extensive computation, we have proved that K can only be either Q or a quadratic extension of Q, to define the arithmetic group. And the absolute value of the discriminant of L is less than or equal to, I think, 1363. So there are not too many possibilities. The discriminant is bounded by 1363, I think. Yeah, okay, 1363, that's correct. So, we content ourselves with, this result. Now, one can try to make a complete list, but we didn't do that. And for A4, the result is that they are fake P4C. In fact, we produce 4 of them, and the list is more or less complete. and then there is a fake Grassmannian of 2 planes in 5-dimensional complex space. So that is a, as you know, this is Hermitian symmetric space of the group PU22, PU23. So you take the group PU23 and its Hermitian symmetric space is the, non-compact space whose compact dual is GR25. So there is a fake analog. So there is a Shimura variety whose cohomology is same as that of the Grassmannian, R of P4C. Okay, and then among A2, there is also a product situation. So which is not product as a variety, but when you go to simply connected cover, so there is a fake P2C times P2C also. And that's the only possibility among arithmetic ones. And it has to be arithmetic because this is rank greater than 1. So there exists fake P2C. So in
These theorems where you say there's a fake, you also know how many fakes there are.
That's right. So we can classify, we can make a list. Yeah. So now, what about the number of fake projective planes? So in fact, all this will involve many number theoretic estimates, and I think I will just illustrate things for type A2. By the way, the type A even is different from type A odd. So that's why we left out complete computation in A3. Because in the volume formula, A even behaves differently from A odd. And that's the only case where this happens. And you can see from Bruhat-Tits theory why this happens. So there is a difference between A even and A odd. Okay, so let us concentrate on the case of A2. So we are looking at PU21, and we are looking at possibly a number field K, which has to be totally real, and L. And PU21 is given by 2 ways. So there could be a division algebra D of degree 3 with center L, or you can have a Hermitian form H on L3. So you can have a 3-dimensional, honest Hermitian space given by a Hermitian form. So G is given by, so our algebraic group. You see there is an arithmetic group, so there is an algebraic group defined over a number field, which is a form of PU21, which means that when I embed K in R in a specific way, then I get PU21, and for any other embedding of K in R, I get compact group PU3. So for any not equal to V0, we get PU3. Okay, in fact, it's better to work with simply connected cover, so I will work with it. Okay, so you will have a division algebra of degree 3 with center L and involution sigma of the second kind. You see, classical groups are all given in terms of central simple algebras and involutions. This is André Weile's famous theorem. So all classical groups arise that way. And in case of PU21, the only possibilities are, of course, K and L could be arbitrary, but then you have to have a division algebra or a Hermitian form, because the degree is a prime number, 3. So you don't have a mixture of the two. Okay? So now the question is, can I classify K, L, D, or H, and then use this to get my gamma, a complete control over my gamma? And the answer turns out to be, yes, and it's given as follows. So first of all, given a gamma, so you see gamma is here in PU21, and I go to its simply connected cover, and luckily this map is on 2. So I lift gamma to gamma tilde, yeah, inside SU21. And you know, this is a real group. Now, gamma tilde acts on, you know, this is arithmetic situation. So it acts on the, so in fact, you know, this is, I'm thinking of SU21 arising from my group over K, and I have fixed an embedding of K in R called V0. So gamma tilde acts on the Bruhat-Tits building at every non-Archimedean place. So the Bruhat-Tits building, you know, may not be two-dimensional. It could be even one-dimensional, because the rank of our group may be sometimes 1, sometimes 2. So the group may not split over a place, and then the rank is 1, and you have a tree. But otherwise, you will get a two-dimensional thing. So I'm just illustrating the whole principle for A2. So in higher dimension, you will have many more possibilities. Okay, so this acts on the building, and then by fixed point theorem of Bruhat-Tits, it always fixes a point. Because see, at a p-adic place, at each p-adic place, at each non-Archimedean place, our group is compact. Yeah, because you know, it's a group inside, arithmetic group inside real group. So at each p-adic place, you know, it's compact. So it fixes a point. So I choose for each V a minimal parahoric normalized by gamma tilde. So gamma tilde fixes a point, which means that the corresponding parahoric is normalized by gamma tilde. So I look at all points which are fixed by gamma tilde, and then look at the point which lies in the largest simplex, yeah, in the interior, and that will give you the smallest parahoric. So for each place P, I am getting a parahoric, you know, and it will turn out that this parahoric, the minimal one, is unique. I mean, it's not a priori clear that it should be, but it's unique, the minimal one. There could be larger ones which are also normalized, but the minimal one is unique. So to gamma tilde, we associate this collection, PV. And now one sees that gamma tilde is then contained in the normalizer of lambda, where lambda is given by this collection of parahoric. So I take inside the finite Adel group, I take the product PV, and this product will be open because PV will be hyperspecial at all but finitely many places. So you think of this inside the Adel group of G, and you look at the intersection of this with the group of k rational points. Because each PV is normalized by gamma tilde, it's clear that gamma tilde normalizes the collection PV, therefore it normalizes lambda, which is given by PV. So this is the normalizer. Now by Galois cohomological considerations, which is done in our paper, one shows that the index of lambda, so lambda was this, so the index of is a 3 to the power something. So the index of lambda in normalizer lambda is 3 to the power something, and in fact we can give you a bound. This is 3 plus cardinal T of places where the group is anisotropic. Yeah, so T naught is the set of places where the group is compact, you know, anisotropic. So there could be several such places depending on the division algebra. And then you will have the class number, but the class number only the 3 torsion part in the class group. So you look at the 3 torsion part in the class group and take the order. that's HL3. And then there is product which comes up in the Bruhat-Tits theory. And so this is somehow the adjoint group acts on the building, and this is how it acts on the diagram, the affine diagram. So this is cardinality at each place, and there are finally many places. Okay, so this is a bound on the normalizer of lambda over lambda. Okay, now the volume formula which I have given computes volumes of things of this form. So if your arithmetic group is intersection of GK with PV, so such a thing I call principal arithmetic group. So it's given by choice of parahorics. And you see, a volume formula must involve some local invariants. Because, for example, SL2, SL2G, the volume is pi squared by 6, up to some normalizer. Why is it so? Because, SL2G, when you complete at a prime P, gives you SL2GP, which on reduction mod P gives you a group over finite field, namely SL2. And the inverse of the order of that, when you take the product, gives you Euler product for zeta 2. So that's the reason why zeta 2 comes up in the volume formula. So you would expect a similar thing in more general setup. So the volume formula for outer type A2 group is, let me write down in all the details, dl by phi by 2 divided out by dk. You remember that there are two fields involved, and then you have zeta k2, and then you have, so this is the Dedekind zeta function for the field k, and then you have HKL function for the quadratic character, and this is evaluated at 3, and this is divided by 16 pi to the power 5, the degree of the field k. I'm assuming that the Tamagawa number is 1, which of course for classical groups was known already long time ago. But for all,
that's your input. That's part of the input.
that's part of the input. So I will assume which is the case over number of fields, and hopefully over function fields with Getz, Gori, and Lurie, that Tamagawa number for simply connected groups is always 1. Okay, and now there is also a fudge factor, E prime. So you have this volume. So the volume of mu gr by lambda is this. What is E prime? E prime is a finite product of positive integers, and this finite product comes about for the following region. You see, these parahorics which were given by our gamma tilde need not be hyperspatial. There is no reason why our fundamental group was so nice that it gives you hyperspatial groups. So sometimes, only finitely many times it will happen that PV will fail to be hyperspatial. There will be also situations where L is ramified over K at a prime, and then hyperspatial will not exist. But then maximal parahorics will exist, and PV may fail to be a maximal parahoric in these places. So if hyperspatial exists and PV is not hyperspatial, then I will have a fudge factor. If PV is maximal at a place where the ramification occurs, then the fudge factor will be 1. But if PV is not maximal at such a place, then I will get an integer. And all these luckily are computable. These are not just some random integers, but they are very precisely computed integers in our field, our paper. So you can actually write down these things, but let's rewrite this. Using functional equation, God cancels out things very well. So the functional equation for zeta and L actually completely takes care of pi and dl and dk. So it just gives you 2 to the power minus 2d, zeta k minus 1, L over k minus 2, and E prime, as I said, is a product of positive integers. Okay, now from Ziegel, Klingen, Ziegel, you know that these are rational numbers. So the whole thing is a rational number. Okay, so the volume, the co-volume of lambda is a rational number, and this rational number is precisely this. But you know, the normalization of R major which I have used in my volume computation is really universal normalization. You know, all of you know how to normalize R major for compact groups, but I think not many know how to normalize R majors for non-compact groups. But there is, there are some people here who.
I think the right way is what you call a Hardy-Littlewood normalization.
Oh, for non-compact groups?
Yeah.
Oh, okay. So I would have to learn that. But you know, the way it's normalized is, you know, it's very quick. You know, I have already given the cat out of the bag. So you see, the point is that you see volume form is given by exterior form of highest degree. So a form here gives me a form in K plus IP also. And therefore, a R major here gives me a R major on the compact dual. And you demand that your R major on G is the one which gives you volume 1 for the compact dual. Okay, so that's the normalization. Okay, so once you have that normalization, then luckily the Euler point array in the orbifold sense, you see lambda could have torsion. So the Euler point array only in the orbifold sense is given by the Euler point array of the compact dual times the volume. So you know, the normalization of R major gives you this. So the Euler point array in our case is 3 times. So you know, this is 3 because compact dual is projective space. So this is 3 times the volume. So now the volume formula together with this formula for Euler point array gives me chi lambda is 3 times 2 times. Okay, and now therefore chi of our gamma tilde, chi of the normalizer of lambda is, so this is going to be, you divide by the index, which we have already said is a power of 3, and I have given you a bound for that. So this number divided by the index is what the Euler point array for normalizer of lambda is. But let us see that our gamma tilde arose from a fake projective plane. So the orbifold Euler point array of the original gamma was 3, and I am working with a 3-seated cover. Therefore, the Euler point array of this is 1. And since this group contains gamma tilde, its Euler point array will be a submultiple of 1. So the Euler point array here, this is a submultiple of 1, which means that it's of the form 1 by some integer. Okay, so now let's look back at this formula. So you have a power of 3 in the denominator, a power of 2 in the denominator, and then you have some rational number. So the first proposition I have already proved is that the numerator of 2 to the power minus 2d zeta k minus 1 L over k minus 2 together with E prime is a power of 3. Because see, any other prime in the numerator will not cancel out with the denominator. So the numerator of this zeta and L function value together with 2 to the power minus 2d and E prime must be a power of 3. In particular, since E prime is an integer, if you drop E prime, still the result holds. So you know, when we make a list, in the final list, we will actually have to compute zeta and L precisely, and then show that the numerator most of the time cannot be a power of 3. So our list gets shortened by this final consideration. So now you see what kind of bounds we have available to us which need to be used. So you know, in the formula, let's go back to the original formula without applying functional equation. So in the original formula here, you have the discriminant of L and discriminant of K, and you have in the denominator something involving class number. As I said, this index is bounded by something involving class number. So for the discriminant, they are bound by Odalisco. So you use these bounds, and these bounds give you bounds on discriminant of L and K, totally real and totally complex fields, and these bounds become better as the degree goes up. So as the degree of the field goes up, the bound become better. And in fact, it's very important because you see, the discriminant of K is roughly, bounded by dl to the power half. So this number is greater than or equal to dl to the power 2. So you have a large power, power 2 of discriminant. So hopefully this factor will not really create any trouble. And you need to, using Odalisco bound, show that this factor, as well as in the denominator, the class number coming up, does not create problem. So for class number, we use the Ziegel-Brouwer bounds. So that bound involves regulator. And for regulator, then we use Zimmert bounds. Brouwer-Ziegel, yeah. Yeah,
You're doing numerics.
Yeah.
Are you assuming Riemann?
No Riemann. So Brouwer-Ziegel in a very effective way. So it's all explained in the paper. Yeah, so it's done there in an effective way. And in fact, I can write down the form of Brouwer-Ziegel we use. So, towards the end. So we use all those to first of all determine the possibilities for K and L. So, you first determine L, and once you have determined L sufficiently well, then once again, for each L, you determine the possibilities for K. But you see, there is class number, and the trick is that the class number which comes in the denominator probably could be very large and may spoil the game, because it's in the denominator. Things may, because of class number, may become small. But if the class number is large, then the Hilbert class field is large. The degree of the Hilbert class field over L is the class number. So if the class number is large, the Hilbert class field is large. But for large field, Odalisco bounds are much better. But for Hilbert class field, the root discriminant is same as the discriminant of the original field. So you have not changed anything by going to Hilbert class field, but you got a better bound. So we use all that and make a list of possible K and L. But once you have made a list of K and L, you are not done, because you still have to see what kind of algebraic groups, which are forms of SU21, can arise from K and L, and for what arithmetic groups you might have the right Euler-Poincare. So as I said, G can arise either from a division algebra or from a Hermitian form. There are two possibilities. D, a central simple division algebra over L, or a Hermitian form on L3. Okay, so if K is Q, then H cannot be the source of our group, because if K is Q, there is only one real place, and at real place the Hermitian form represents 0 because it's SU21, and a Hermitian form which represents 0 at a real place, the unique real place, then by Mayer's theorem, I am working with 6 or more variable quadratic form, 3 or more variable Hermitian form. So by Mayer's theorem, it will represent 0 globally. So it's an isotropic group. By Godema criterion, you will not get a co-compact arithmetic group. So if K is Q, you are very happy. You have ruled out the possibility for H. So over K equals Q, which happens often, you must work with a cubic division algebra. Now by class field theory, you know that a global division algebra is determined by its local indices. So I must determine the local indices of D. It may ramify at lots of primes. And then you have very complicated situation, more it ramifies, more problem you have. So you must determine the division algebra uniquely, if possible, and then go on to list PVs, the parahoric subgroups. So what happens is that if a division algebra ramifies at a prime, then at that prime the group is compact, and the only parahoric which exists at that prime is Ivahori. There are no larger parahorics because the building is single point. So there is only one Ivahori. And you know, this is ideally the situation which contributes to E prime. So if you go, the contribution of a ramified prime for division algebra is roughly of the order of residue field raised to the power 3. So if 7 is ramified, then you will at least get 7 to the power 3. But if 19 is ramified, you will get even a much larger factor. So more the ramification, larger the factor in E prime is. And if you have 7 different ramification places, you see E prime will blow up. So finally, we prove that our division algebra can ramify at a unique place. And that place we can determine because the contribution of each place to E prime is totally computed. So we know, in fact, K equals Q gives us lots of places, lots of examples, and we know that, for example, Q square root minus 1, which Mumford method would not have ever given us anything. So our division algebra for this pair should ramify at prime 5. Okay, and then you have then a list of division algebra because I know the ramification places. And you know, this is a cubic division algebra, so the local index can either be 1 over 3 or 2 over 3. You see, it's a cubic division algebra, or 0 if it's split. So 1 over 3 and 2 over 3 are same division algebras because one is opposite of the other. So it doesn't really matter which one you choose. So in any case, the upshot is that over K equals Q, Hermitian form does not exist and division algebra can be classified. And if K is not Q, which originally we had 40 pairs, K and L, for which K was quadratic, cubic, or biquadratic extension, totally real, and L was a quadratic extension of K. So out of those 40 pairs, we computed exactly zeta and L values in each of those 40 cases. You know, now with Pari, etc., you can compute things up to a large degree of accuracy, and then by rationality and bound on the denominator, you know what the exact number is. So we computed, and it's listed in our paper, each of these numbers, and then showed that the numerator cannot be a power of 3 except in 4 cases. You know, and then there were other considerations. You know, some cases were eliminated because arithmetic groups must contain torsion. You know, we are dealing with, this is very interesting. You all know Selberg's theorem that if you go deep enough, it's torsion free. But you know, if you go deep enough, then Euler-Poincare increases. So you have a tension going deep enough or staying, on the surface, and then you have torsion. So you play with this tension, and you find that by going deep enough to remove torsion, you are increasing the Euler-Poincare in an unacceptable way. So finally, you get a list, and this list then is very short. So you get 28 families, which includes the pair KL, the possible division algebras, the possible parahoric subgroups. So you consider this tuple of, 4 tuple of KL division algebras and parahorics, you will get exactly 28 families of acceptable, possible. And for each one of them, we actually show a explicit arithmetic group which gives you the fake projective plane. And then, so which means that we get 28 non-empty families. And this is the classification. So the classification is in terms of KL, division algebra, involution, and PV. And then we also say that there cannot be a H giving rise to a fake projective plane even when K is not Q. And that's more tricky, to eliminate. K equals Q was Myers theorem, Godema criterion. But if K is not Q, there could be another real place where the group is compact. PU21 becomes PU3. And that, therefore, does not rule out the possibility for H. So this has to be done in a more, in a cleverer way. But we are able to do that, except one case which I called C11, and I wrote down that Q square root 3, Q zeta 12. So in this particular case, there could be a Hermitian form over L3 for which you have no problem so far. Namely, there could, in principle, exist a fundamental group whose order Poincare is exactly 3. But this fundamental group will sit inside the volume computation done in our paper showed that this index of our fundamental group inside the normalizer is 864. Now, to produce a subgroup of this index, which is torsion-free and so on, is not a joke. So now it brings me to Cartwright-Steger work. So you see, once we classified these fake projective planes, and since the algebraic geometers working in algebraic surface theory were so interested, we actually worked out a plan about computing each of these families. So in each family, we showed at least one very symmetric surface. And then the question is how many more in each family there exist. So that required a computation of the following kind. You look at the normalizer, and our fundamental group sits inside there as a subgroup of a correct index so that you get the correct Euler Poincare. So Cartwright and Steger, by constructing fundamental domain for normalizer of lambda, they could write down generators and relations. It took 3 years of computer time. And they could write down for each of these 28 families, they could write down generators and relations. Usually the groups were 3 generated and a very small number of relations. So they could write down in each case, by hard computations, the generators and relations, and then up to index 50, you have magma, which can give you, once you know generators and relations, up to index 50, it can produce subgroups of given index up to 50. But 864 is something which magma or no known program can handle, even knowing generators and relations. But they found some theoretical and computational tricks to handle that index, and they finally came up with one example of index 864, in fact a unique one, which gives you a surface, and they computed the Betti number of this surface, H1, and it turned out to be G direct sum G. So Betti number was 2. And in each of these 28 families, altogether contain 50 fundamental groups. So there are not too many. The examples we produced were almost complete. Out of 28, we produced in some families 2 or 3. So we produced several, but in each family there were sometimes more than one, and they constructed 50. And each one carries 2 complex structures, complex conjugate and complex. So there were exactly 100 fake projective planes up to biholomorphisms. And they discovered many interesting properties, and our theoretical argument already gave that H1, which is vanishing with R coefficient, over G it does not vanish. So no fake projective plane can have vanishing H1. There is always torsion present. And we can actually give a bound on torsion, and now with computations, you know exactly what this torsion is. So in particular, complex P2 is the unique surface with the homology equal to what it is. So if you get a complex algebraic surface, a smooth one, whose homology is same as that of P2, then it is P2. So P2 is determined totally by its integral homology. So that's also a consequence of our work. Yeah, and there are many other things, for example, about line bundles, embedding, but there is not much time left here too.